You want to present on my machine or your machine? Okay, do you have something on CodeCalc you're trying to show? Okay, so why don't you pull that up on your computer and I'll put the book up here and we can go between the two and then I'll just let you share your screen when you're ready. Yeah, that's okay. Whoever's really relaxed. Okay, so where do you want me to start? You want me to start with your examples or do you want to start with the text?
And then just throw the examples in the way.
Okay. Okay. And how many people here? 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have almost everyone here. Getting feedback to you is a little tricky through CodeCalc. So the way that I normally like to do it is I would like the original couple times that I taught this class, I would just like give you a grade. But now I'm realizing that with ungrading, it's quite hard because there's no way to communicate to you like line 47 is wrong. So what I want to do is I want to check in with all of you next week. Okay. So that's a 15-minute conversation about where you are in the class that you schedule. Okay. Next Friday, I won't have office hours, but everything else is normal. So let me know what works for you. The sooner you sign up for any time to meet with me, the better. If you haven't been doing the homework, do the homework. I know you're mostly doing the pair programming, which is great because you're forced to. But it's easy not to do the homework. You're like, oh, I'll put that off till next week. Don't do that. Okay. Questions, comments, concerns? Not during class. I can't take time away from class to do it, but I can do it anytime outside of class. And I can create extra time if you can't make any of the office hours. It can even be online. Okay. Okay, sorry, let me go all the way to ODEs. Okay. Look at us go. You ready? Yeah, no rush, no rush. How's everyone else doing? Good. Now it's a lot of ups and non-responses. Okay, let me start by asking a question. What's this first word mean? That's what you read, but what does it mean? Nope. That is true. That is definitely a definition, but it's not the one here, right? Again, those would be the same interpretations. That's not the mathematical definition of ordinary. Yeah.
Variable, the function just has like x, not x, y, z. Ordinary.
Ordinary means you're taking derivatives and that function is only of that derivative. So when you have this beautiful little d, your standard looking d, that's an ordinary differential. You've never called it that. You just called that the derivative. But you know what its brother is? The partial. So there are partial differential equations and ordinary differential equations. And that's the difference. What's the last word here?
Wait,
Good. What does that mean?
it means like two things that are equal to each other.
Good. What's this? What does that mean?
Written.
What does that mean? Yeah, there needs to be rates of change in the equation. And they must.
Consist of only one variable.
So you have one controlling variable, right? This is the simplest form of the differential equation, right? Everyone happy? Okay, ready?
Oh, how would I put my code count on the screen?
So when you're ready, you'll share, and then I'll just give you, I'll stop presenting here and I'll put it up here.
Okay.
Like when you're ready, you can share your screen, and then I will put it up from my computer. Once we get to a point with your example, I'll show you. Yeah. Yeah, go ahead.
So today we're going to talk about ordinary differential equations. And we're gonna start with first order ordinary differential equation with one variable. So as you can see in this example, so this is like the simplest type of ordinary differential equation, which is with one dependent variable. And these kind of things can pretty much be solved analytically by separating the variables. But let's say we got an equation like in the second one, which has like, well, well, as soon as it gets to that, like it's gonna be really hard to solve it analytically because it's not easy to separate, and plus it's non-linear. So, and this is when we use the computers, because although it's hard to solve it analytically, it is not as hard to solve it numerically. So to do this, first we can use Euler's method. So it's gonna look like, oh, it's in the next page, sorry. Yeah, so Euler's method, it looks like the equation below. And yeah, if you say dy over dx is f of xy, we're gonna take a Taylor expansion around x of t plus h. And which can be written as the equation below, the x of t plus h times f of x plus t plus o of h squared, where o of h squared is a shorthand term for the order of h with 2 and above. And it comes down to this equation below, 8.6. And you can see that we have omitted O of h squared. Because as h gets smaller and smaller, since it's a h squared, it gets decently small enough so that you can neglect it. And therefore your equation comes down to x of t plus h equals x of t plus h times f x of t. And yeah. And how we can solve using code is.
So before we jump into the code, does conceptually it make sense what Angeli's showing here? What is the concept behind Euler's method, not the math?
Like you're maybe something like a little bit higher order than ordinary, so it looks and seems ordinary, or it is.
Not exactly. Because we can do this with nonlinear equations. The functional form of f doesn't matter. Right? We're going to say something like f, and sorry, I'm going to derail you just for a little second because this is important. Okay. So f is something d dt, right? Oh, sorry, I did this wrong. D, what do they say? F or X? Let's call it that one, right? Oh my God. Right? So that's some function of x. That's the derivative. And what does that mean again?
Rate of change.
Good, and what does that mean again? Conceptually? The slope. And here's really, really where I want you to think about the geometric, the intuitive sense of what we're talking about. Because what we're going to do is we're going to think about this geometrically. You have some function. Okay? You start at a point, x of t. You want to move to the right, increase time. So you start with x, and what's the derivative of x with respect to t? Let's do this differently. Hold on. I'm going to draw an analogy, and then you're going to see it. What's that thing called? What was that? The velocity, right? That looks a lot like a velocity. So I start at x of t, and what does that say over there? It says x of t plus h is this plus the velocity times a little bit of time, where h is your time step, right? So what you do is you conceptually start at a given location, you calculate the derivative there, and then you shoot. And then you move, calculate a new derivative, and shoot. Right? Okay. That's the concept. And of course, we'll see it used not only in terms of x and t, but you can see this in space as well. The curvature tells you. Okay, go ahead.
So the code to perform this calculation is gonna be that, and I'm gonna go to my code calc.
Okay, I'll stop screen sharing and I'll let you share. Are you sharing? Are you on Zoom? Oh, you have to be on Zoom.
Okay.
And then you can share. Oh. In LA? Yeah. Not in San Bernardino. Southern California. First, I did undergrad at Santa Cruz. So that was my first leaving Southern California. And then big difference. Lots of rain, coldness, which we don't have down here. And then I went to Colorado and it was very cold for 6 years. And this thing called snow just falls on the ground. It's crazy. You got to shovel your fucking driveway in order to get out. It's wild. And then I went to DC and it was horrible.
You didn't like DC?
No, I love DC, but the weather there is like the worst. Because there's this thing called humidity. It's like where there's like moisture in the air. And it makes any time that you're warm worse. Because you can't take your skin off. You can put clothes on. You know, you can put on like a big old jacket. You're like, oh, this is nice. But like once it's like 80, 90 degrees with 100% humidity, you're like, what? So yeah, everything's sticky. And like I would walk to and from my apartment and it would be raining outside, and you're thinking, oh, that's not so bad. You know, you have a rain jacket, but it'd be like this really wet, thick rain, and somehow it'd like get through your rain jacket. You're like, how? I use this in snow. Okay, good. What is this? Wow.
Sorry about that. So this is example 8.1 using Euler's method. So let's say we're solving a differential equation, which is negative x to the power 3 plus sine t. And we're doing dx over t dt. So we import all the stuff we need to do this math. And from math, we import sine. And from NumPy, we import a range. And from PyLab, we import all the stuff that you need to plot the graph, because we're trying to plot the graph using this function. And so first we define our equation, saying define f of xt, which is equal to this, returning this equation that we're solving for. And we set the initial condition, which are, so A and B are the two limits. So A is the starting point and B is the ending point of the interval. And you have your number of steps here, and this calculates the size of a single step, which is interval over a number of steps. And we set x is equal to 0 for initial condition, because we're going to start adding stuff into the array. And then we set one variable to equal, we call one variable t points is, and we set it to a range, a comma b comma h. So what a range does is that it takes, it basically spits out it creates an array for consistent of evenly spaced value within given intervals. So this part takes the start of the interval, and this part, this part is the end of the interval, and this is going to be the step size. And I'm not sure if it's important, but why we use why do we use a range instead of range? But actually, range does the same job, like if you really wanted to do it. So with a range, a range is pretty similar to range. You set the starting point, you set the ending point, and in increments of the certain value that you set here, which is in default 1, and the default starting point is 0, and it will spit out all the number in that interval right before the number of the ending point. So if you set a range 5, what would it produce? What number would it produce? A range 5.
0, 1, 2, 3, 4.
Yes, awesome. Yeah. So basically it's similar to range. It's gonna work like range, but the only difference is it's gonna produce a NumPy array. And also a range can deal with can also deal with floats, whereas a range cannot. Range will only take integers, I think. And so in this case, why we use a range is because our step size is actually going to be a float. It's going to be a decimal, and we can use range. And also a range can be used without the for loop. And we're not using I guess we can use line space here. I tried it too, but it pretty much produces the same result. But I think why we're not using line space here is because our objectives are different. I guess we are not intending to spit out a number line that's evenly spaced, but rather we are trying to create numbers in incrementals this specific step size.
That's the only thing I'll quote for a second. only thing I'll say about this one versus this one, lens space, for example, is A through B with a certain number of steps. And you already saw this from the last homework, right? That you wanted to create this thing. So it really depends on what you started with. Did you start with the step size or did you start with the number of steps, right? And that might be the reason why you choose one of these two. But as Angela was just saying, if you choose T points with a defined step size, that's perfectly okay.
Yeah, and if I would print the T points, so you can see it's starting from 0 with increment of 0.01 because that's a step size, and it's gonna end at 0, it's gonna end at 9.99 without reaching 10, right before the ending value. So, and that's that. And there is another variable x point, which is set to a blank array. So here we're gonna create a for loop, and for each value of t in the array of t points, it's gonna calculate the x to h times f of xt. And so basically it's gonna take t out of every number in the t points and plug it into this calculation and obtain x. And there is an x points append, which is gonna return the value into this blank list. And you do this function and you plot the graph and show it's gonna give you a nice curve like this. And that's this example, yeah.
Okay, so let's pause there for a second. People understand how we're doing this?
The append before that one.
Good question.
No.
Did you hear the question?
I asked why is the append for x points before the equation?
I didn't really think about that. Does it matter? It matters.
This has sort of a snarky answer, and that just has to do with the fact that you didn't stick X points in at the beginning. So for example, you made it empty, and then you have your initial condition. And the very first thing that you would do is you would append it so that the initial condition is recorded. And then because this is plus equal, this updates it. Whereas if you flip them, then you would lose any information about that initial condition. So in practice, we have the append at the beginning of the step, but that's only so that we don't have to do it somewhere else. Any other questions? Because if you don't get Euler's method, you won't get any of the two harder methods that we'll attempt to do today. Okay? Okay, should we go back to the text?
So okay, so but the thing is, ideally we don't use Euler's method in real life because, well, the Euler's method, it eliminates, it kind of neglects all the I guess the error. Well, all the h from the second power and above, and it just makes it a very broad approximation. So there is more accurate, I guess, more an improved version of Euler's method, which is called the Runge-Kutta method. I'm gonna say it's RK because it sounds a bit long. I don't know, it's a bit long. Okay, so basically, this is the more accurate version of the Euler's method, and it's basically like a set of mathematical technique used to solve differential by taking multiple test slopes at different points within an interval. So a good way to think about it is like, imagine you're trying to map a path of a winding road. You're trying to take this like a turn at a winding road, and the Euler's method, it will just like check your current direction and will take a huge leap from that point, which is not a very good way to take a turn, and you will miss the turn. And compared to that, the Runge-Kutta method, so it will check your direction at multiple points of the curve and make small adjustments each time, and which will represent the curvature better. So that's kind of like the analogy. Yes, so it's the formula. If we go to the next page. Yes.
Yeah, you don't have to show the derivation at all. We can just talk about this.
Okay, so basically it takes Taylor's expansion around a different variable now. So but like if you kind of like ignore all the derivation, we come down to x of we come down to the equation at 8.12. With pretty much similar, but with few added variable, and now instead of L of h squared, it's L of h cubed, which is more accurate than before, because as h becomes smaller, it will become even smaller than it was when it was an x squared. And for simplicity, we can write this equation as how is it 8.13 to 8.13. So we're gonna write it like this, and we can rewrite the x of t plus h to x of t plus k2. And if we go to the next page,
Well, do you want to explain how this works? Or are you gonna show the code? What do you prefer?
I'm gonna go into the example.
Okay.
Yeah. So, yeah, that page basically talks about how we have how we have to approximate the x of t to the power half h using Euler's method, and it's basically saying that even if you do so, the error wouldn't be as much of an issue. But when we go into the example, and I will share the screen again. It's example 8.2. So now we're solving the same equation, same derivatives, so using the second order arcane method. So the code is pretty much the same. We import the same kind of stuff. The initial conditions are the same, except that the step size is 10 right now. But
The step size is 10?
sorry, the number of steps is 10. Thank you.
Yeah, good.
Yeah, so we're gonna do the same thing. Yes, never mind. And the difference is that in for loop, now there is this k1 equals basically this part that was like newly added to the equation. And we're gonna keep appending this calculation into the blank list of x points. And if we hit show, it's gonna give you a not very smooth graph. It's kind of wonky and edgy, but that's because the step size, the number of steps are so small, it's 10. So what if we increase it up to 50? Oh, did I? Oh, maybe I did something else. So if okay, cool. So if I increase it to 50, it's gonna give you a nice smooth curve that looks exactly like how you got it using Euler's. And if I would compare the two graphs over here,
It hasn't done RK4 yet.
oh, I see.
It's okay. We can get to that later.
Okay.
Why don't you explain what K1 and K2 is for folks who don't know what that is yet?
Oh, sorry, what was that?
What is K1 and K2? Can you show them?
Oh, yeah.
How do we interpret those two things?
So,
Yeah, just scroll up a little bit so you can see.
From my understanding, it's how they derived the formula. So they first took the Taylor's expansion around x of t plus h. Then they derived the expression for x of t, and they subtracted the second one from the first one and rearranged it to get this formula. And K1, I believe it's is it the first?
Scroll up really quickly.
Oh, for the code? Oh,
Yeah.
sorry.
Yeah. Okay, so we can read it, right? So K1 here means what? What's K1? Yeah, yeah, it's certainly a point on the graph multiplied by the subset. Think about it in terms of Euler's equation. What was it in Euler's equation? We wrote it on the board. The slope times this time step, right? Or like the velocity times time, however you want to think about it. So K1 is your Euler step, right? But then you don't take it, right? This is not plus equals K1. This is find K1. And then what do you do? What?
Composite function of the Euler step.
Yeah, you only take half of the Euler step. So you calculate the Euler step, and then you only take half of it. You see? And they claim that that's better than Euler. And of course, you'll demonstrate that today. Does that make sense? So, yeah, so one thing that you'll fuck around with today is that if you change, say, how big your time step is, you're thinking to yourself, oh, this is easy. I'll just make my time step half as large. That'll be just as good. And then I won't have to code anything new. And you'll be wrong. Because what we're dealing with here is not numerical error, but hopefully not. Approximation error. And the approximation error is getting smaller when the terms go as h cubed. If you can eliminate all terms of h squared, you've already done better for the same h, right? Okay. You're a little, I don't want to, keep you for the entire 2 hours. So do you have more things that you want to show, or do you want?
Yeah, 8.3. I think I can just go straight into the example because
Why don't we just let folks play with it? Because I think that's going to let them get a good intuitive sense for how this works. For today, do you want to give me back the screen? If you just stop sharing, it'll work. Yep, thank you. So what we'll do today is, where did it go? Wait. Oh, I was looking down here. Whoops. Okay. So today we'll do 8.1. And this is sort of our first example into using differential equations numerically. And we're going to apply this system to these sets of equations here. It doesn't really matter what they mean, right? We're going to use physics in this particular context as a stand-in. We care about the differential equation. So if you have questions about why the differential equation looks that way, I'll refer you to Physics 2510. But if you're curious how it works on the computer, that's what we should talk about here. We don't want to get bogged down in understanding the nuts and bolts of the problem when we just care about finding the solution. Does that make sense? Okay, so it's a very straightforward day. We're going to code something twice. You're going to code it once with your Euler method. So it says here to use fourth order Runge kutta. Don't. Listen to me when I tell you, start with Euler. Okay? If you did the example, it's a very small change. So I might even recommend that you start with the example, right? And then once you've made that small change, then you can implement RK2, which is the one that Angeli just showed. And then you can do RK4. Does that make sense? If you jump to RK4, I'm going to be cranky. Okay? Break.